All right, let's do this thing. It's
Let's
not
do it.
Wednesday, but I'm wearing pink. I got this shirt the other day. Can you see the back?
Puppy love.
Puppy love. Rescues are the best breed.
Mm.
All right, let's do this thing. All right, today we are wrapping up our mini unit on sets and proofs with a kind of advanced topic, but it will kind of breach its way into many of the topics that we do from here on out. Groups and their properties. Ready?
Ready.
All right, I don't have my pen. Let me pause real quick. I just realized right
I have my pen here.
Wait. Whoa, that was crazy. How did we do that? We're recording, right? Okay. All right. So, a binary system. Do you know what that is?
That's where there's two things in it.
A binary system.
You have 1 or 0 usually.
Yeah, well, so, okay, that's not really what I mean, but like binary, 1, 0, two things. Bicycle, 2 wheels, binary, two things. A binary system is let's use the word couple, meaning two, of things. There's a set and an operation. That operation must be a binary operation. What is a binary operation? Do you know what a binary operation is?
I do not.
So a binary operation is something that takes in two things and outputs one.
No.
I
so
guess
like 1 plus 1 equals 2.
Yeah. So addition is a binary operation. So like that's an example of a binary operation that we know that's over the real numbers. Subtraction, it's a binary operation. Multiplication, it is. Can you think of anything that's like trinary? I don't know if that's a word, but something that takes in 3 things and outputs 1. I don't know. It doesn't matter. You know what? It's a fun binary operation. Rock, paper, scissors.
Oh, because you put in 2 things, but then you get out a winner or a loser.
Exactly. Yeah. So like rock. Ready? Rock, paper, scissors. Shoot, that was really hard to do on Zoom. You win though. I did scissors. All right. So a rock versus scissors outputs rock. And so rock, paper, scissors is a binary operation. It's something that takes in 2 things and then combines them somehow. Right? So a binary system is a set coupled with an operation. I'm going to use like a star for the meaning of operation. It could be anything: addition, subtraction, multiplication. It could be division. It could be rock, paper, scissors. Let's go bam for that. All right. So enter clock arithmetic. Clock arithmetic is an example of a binary system. Clock arithmetic takes the numbers on the clock. That's our set. What is that set?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And that's it.
Yeah. No 0. We go all up to 12. No 13. This isn't military time. 1 through 12. So it takes that and it has the operation clock. Let's see if I can draw a nice little clock. Does that look like a clock?
Oh, yeah. It totally looks like a clock.
Okay. This is clock arithmetic. It takes a number on the clock. And then it's a binary operation. So you take 2 things. So give me 2 numbers on the clock.
3 and 12.
So 3 clock. I like using clock as a verb, by the way. It makes me happy. 3 clock 12. Fix that. My computer lagged a little bit. 3 clock 12. My computer's lagging right now. So you start at 3 o'clock, which is over here for me. I'm not sure if that's right for you.
Mm-hmm.
And you go 12 on the clock. So if I go forward 12 hours on the clock, what do I get?
Oh, you get 3 again.
You got 3, yeah. So 3 clock 12 is 3. Give me 2 more elements in the set with the operation clock.
So we do like 2 and 11.
11. So 2, move forward 11. That's going to be 1, right?
Mm-hmm.
Yeah, 1. Sweet. Awesome. That is equal to 1. All right. So this binary system takes in 2 things, outputs another thing. It has certain properties that I want to explore. So the first property is this thing called closure. Closure means, or a binary system has closure if you take any two elements and you clock them or you operate on them with your binary operation, and you get a new element that is in the set.
The set S, the same set that we're
the same set. Thank you. Yeah, thank you. So if you take any two elements in the set S and you clock them, must you get something that is in the set, or can you get something outside of the set? We are closed. We have closure if we can only get elements that are in the set. So is clock arithmetic closed? Does it have closure?
I think so.
I think, okay, we don't need
go
to do
around again, right?
Yeah.
So then as we go around, like we got, like if you do like 2 plus 11, you get 13, right? But then with our clock arithmetic, what we do is we don't get 13, we get 1 because we looped back. Which
is in the set. So you're telling me that clock arithmetic is closed under this operation clock, or the set 1 through 12 is closed under the operation clock. The set 1 through 12 under the operation addition is not closed. If you take there are many combinations of numbers between 1 and 12 that when you add them, you get something outside of 1 through 12, but not clock arithmetic, because we come right back around on that clock. Tick tock, tick tock. So we are closed. We have closure. We're going to explore 5 terms. So we have closure. The next thing I want to look at is associativity. Let me spell this thing out. Hopefully I can spell it right. Associativity. Right. Associativity says this: take any 3 elements in the set. Well, actually, give me 3 elements. Give me 3 elements instead of A's and B's. Let's not get abstract yet.
7. 2. 4.
4. Right. 7, 2, 4. So associativity asks the question, does grouping matter? So if I put parentheses around the 7 and the 2, and I clock them, and then I clock with 4, will that be the same as if I clock the 2 and the 4 first, and then clock with the 7? So let's convince ourselves whether or not the clock arithmetic has associativity.
Okay, so 7 clock 2 is 9.
Okay.
And then 9 clock 4 is 2.
9, 10, 11, 12, 1.
1.
Right? Yeah. Woo.
Oh,
I just deleted a bunch of things. What was the number that was? 4, 2.
4. And 2.
4.
It's over there.
And then this ends up being, my eraser still weird.
1.
1. All right, and now I think like the odd principle of addition still works with the clock. 2 clock 4 is
6.
6.
And then 7 clock 6 is again 1.
Awesome. So with one example in math, one example is not usually a good way to prove something, but we're going to sit here and just understand the idea of associativity. Clock arithmetic has this property of associativity. The next thing I want to look at is something called an identity element. The identity element, oh, by the way, we do have associativity, check mark. The identity element is, does the set have an element that when you operate it with anything else, it doesn't change the other thing?
So like you put something and clock it with an element, and then you get the original thing.
Yeah, so if, like, is there an element in this set that like if I clock it with 4, I get 4?
12.
12. Now, follow up, will 12 do that for every element?
Yes.
Yes, right? 5 o'clock 12 is 5, 6 o'clock 12 is 6. You're just moving forward 12 hours. It's PM instead of AM now, but we ignore the AM and the PM. But we do have an identity element, 12. 12 clock anything is that thing. Right, so we have the identity element. We have an identity element in this set. You might know some other identity elements. What is the identity element for the numbers and addition?
0, right? If you add 0 to anything, then you get out the same thing.
Yeah. And how about like multiplication?
That's a 1. When we multiply by 1, doesn't change it.
Does subtraction have an identity? I think so. Yeah, 0, 2, right?
Cool. 0 also.
So this set does have the identity element of 12. 12 clock, anything in the set gives me the thing that we clock 12 with. It's kind of hard for me to say. I probably should commit some time to thinking of a better way to phrase it. Anyways, two more, but one property that ties in with the identity called an inverse element. An inverse element. Do you know what an inverse is?
Inverse is where your input and your output are swapped.
Your input and your output are swapped. Okay, that would be inverses in terms of functions, which does tie to this. But an inverse element in terms of a binary system is an element, or does every element have another element, which we denote a to like the -1, where you get the aforementioned identity element. Yeah, Jinx.
Oh. So that's like composition of functions then, huh?
Kind of, yeah. Like when you compose to, wait.
Because you get out the identity element of X when you have F composed with G.
The identity function X, when you compose two functions, you get X. That's why they're called inverses. Because when you compose them, that binary operation of composition, you get the identity function of X. Wait, does clock arithmetic have an inverse element for every element?
Like, can we get 12?
Yeah, let's just check it. What's 1's inverse?
11.
That gives us 12. Cool. Does 2 have an inverse?
Yeah, I think it's 10.
3.
7. Just kidding. 9.
4.
8.
8. 5.
7.
And then 6.
6.
6. And actually, the property of inverse elements is that they're inverses of each other. So you can switch the order.
Oh, yeah.
11, 1, 10, 2, et cetera, et cetera. I get kind of lazy after I've written the clock a lot. And I just like do a circle with a plus. Don't tell anyone. I am a completionist. Okay. We have 4 properties here. Closure, associativity. We had an identity element. We couldn't ask the question inverse elements without having an identity element. Right? But we have 4 properties. Any binary system that meets these 4 properties is called a group. Why are they called a group? But that is the case. If you meet these 4 properties, you're called a group. There is one more property that's not required for a group. Do you know what that is?
Commutativity. Commutativity.
So I'm going to put a little bar here. Group. Yay. Okay. But down here, commutativity. What is commutativity?
That's where the order doesn't matter.
Yeah. Given any 2 elements, is A clock B equal to B clock A? And I believe that's the case here, right?
Yeah, I think so.
3 o'clock, you move forward 10, you're at 1 o'clock. 10 o'clock, you move forward 3, you're at 1 o'clock. Commutativity, we have that property. Mm-hmm. The order doesn't matter. Fun little story. There's a student from our school that was on Jeopardy. Eric Agard. Do you know the name?
Yep. I think he was in Silver Chips recently.
That's true. Yeah, he wrote the puzzle most recently for I believe, the crossword. I haven't got my hands on a copy yet. But anyways, there was a math category. And all the teachers were like, oh my gosh, we have like a stake in this game. And he got almost, maybe if not all of them, wrong. Which goes to show, like, some of the things we learn in high school don't really matter. But you didn't hear me say that. But like, I think like it was a couple $1,000s that he didn't get because one of the questions was, what is it called when you switch the order? And he said, associativity.
It's okay.
Yeah, but it's okay. I mean, if you've ever needed a reason to know this content, you might be on Jeopardy one day, of which there is a round dedicated to math. The odds of that, very small.
Do they reuse Jeopardy questions?
I don't think so.
So then everyone's safe.
Nah, but like they might rephrase the question. I don't know. Doesn't matter. Anyways, if the group also meets commutativity, it's called an abelian group. Probably named after someone. There's a journal idea. Yeah. Learn about abelian? Maybe. Yeah. Sounds like an alien from like Star Trek. Anyways, this is the idea of this lesson. Group theory and being able to show, does a binary system meet these requirements? These are the things that we want you to understand. Closure, associativity, the identity, the idea of an identity, the existence of an identity. With that said, inverses that give you the identity, and also commutativity. Hard word to say, in my opinion. Hey, guess what?
What?
What's purple and commutes? Oh, you crabbed me.
The purple crab.
A purple crab? Wait, a crab commutes? I don't think so. If it turns around, doesn't look the same.
But it can go backwards and forward.
That's true. Well, that's not what commutativity is. It needs to switch. Wait, what's purple and commutes? Is that your best guess?
Yes.
All right. The answer is an abelian grape. Okay, let's keep going. All right, let's look at the group axioms. These things that we just talked about, written in math text. All these symbols that we've been looking at all year, and then let's get into some a little bit less silly examples. All right, here we have 2, 4, 6, 8, and the operation money sign. I just said, let's be serious. And then that's what happened. Group axioms, closure. Can you read this math sentence for us?
Oh, yeah. So we have, we are also establishing that we have the binary operation of the set A with the star operation.
Yeah, so what does that operation do? We don't know. Doesn't matter. We're just using that symbol.
So we have a group if and only if. We have closure, which is for all X and for all Y. X star Y is an element of our set A. Associativity, we introduce another element. So we have for all X, for all Y, and for all Z, X star, the grouped operations Y star Z is equal to the grouped operations X star Y star Z. And that long pause was to close that parenthesis. And then it's the backwards E thing, which is existence. I don't know if we have talked about that yet, but there exists element Y for all X, such that we have X star Y equals Y star X equals X. So we get out our original thing that we were looking at, because they were saying that there exists a Y element that is our identity element for that X.
Can I say something real quick?
Yeah.
Just want to point out, all right, we're going to get to commutativity in a second. Commutativity is not required for a group. However, it is required for the identity portion of the group.
So like, just like you were writing like 12 clock stuff, but then you could also write that as something clock 12.
Exactly, yeah. All right, keep going.
And then the existence of inverses. So for all X elements, there exists an element Y such that X star Y equals Y star X equals our identity element.
Awesome. We didn't reuse the letter Y there, so that's why we wrote id instead of Y again.
Yep.
Awesome. And then last but not least, a commutative group.
Oh, for abelian group. So we got a commutative group or abelian group when we have commutativity, which is for all X and for all Y. x star y equals y star x. So that means we can flip the order and be okay for anything, not just with our inverse element, our identity element.
I guess the only thing I'll add to your wonderful reading is that if this interests anyone, before we get into some more of this, there's even more structured groups with even more requirements and more vocabulary if this is something that interests you. There are things called fields. That's the only one I can think of, actually. But we have higher order binary systems if anyone wants to look into that. Just go on Wikipedia or something and type in group axioms. You'll easily find a hyperlink to higher level stuff. Let's do an example.
Cool. Money.
All right. So do you know what this table is called?
Money.
Money. Well, so I don't know why I remember this, but I remember this very vividly from my Math 310 class in college. But this is called a Cayley table.
Maybe named after someone named Cayley.
Probably. People like to name things that a lot of conceitedness. I don't know. Anyways, in the mathematics world, this is a Cayley table. It helps us look at whether or not a binary system is a group because it possesses certain qualities when we fill it out. Let's look at this. So when we fill this table out, this is going to be our first element, and this is going to be our second element when we fill out a box. So for example, this box right here, it would be 2, specifically this 2, money sign this 2.
Okay. Maybe that was a bad example.
That was a bad example. Yeah. So these two boxes are slightly different.
Okay.
This is a better example. This upper star is 2, money 4. This lower star is 4, money 2. Why might I bring this up?
Because sometimes the order does matter.
Yeah.
Right.
Let's see. 2, 4, 6, 8. Money outputs the ones digit after taking the product of A and B.
Okay.
So 2, money 2. It's going to be 4, right? Yeah. 2, money 4.
That's 8.
2, money 6.
2.
It's 12, but we take the ones digit. And then 2, money 8.
6.
6. Right. Now, 4, money 2.
8.
8. And 6, money 2.
Oh, we're going down.
Yeah. Oh, I can go across. 4, money 4.
6.
Okay. 4, money 6. Now the numbers are getting bigger.
4.
4. And 4, money 8.
2.
2. 32.
32.
Yeah. All right. 6, money 2.
2.
Hey, on the next, we have 2 examples here. On the next one, we'll fill this out together.
Okay.
6, money 4.
4.
4. I see a pattern here, by the way. I don't know if you see it. 6, comma 6. 6, money 6.
6, money 6 is 6.
And then 6, money 8.
8.
8. Okay. It looks like we have a lot of these operations. 8, money 2. Sounds like you just noticed something.
6.
8, money 4.
2.
8, money 6.
8.
And 8, money 8.
4.
4. Boom. All right, let's inspect this thing.
Okay.
Are we closed?
I think so.
Yeah, we're closed by like sheer exhaustion of checking, right? We looked at every possibility.
Uh-huh.
And we're closed. Sweet. Okay. I'm gonna write yes, not check. Yes. All right. Are we associative? This one's harder to check.
So we have we have 2, money 4.
Let's do an example and convince ourselves one way or the other. So arbitrarily choose like 3 numbers.
2, 4, and 8.
2, 4, and 8. Let me write an 8 like an 8. Money. Does this money sign have 2? Oh, only has 1 slash through it. That matters significantly. 2, money, 4, money, 8. Let's throw some parentheses in here. You want to do the left-hand side? I'll do the right-hand side. Is that possible?
I'm doing the left-hand side?
Yeah, okay. I'll do the right-hand side.
Hey, boom.
Boom. Boom. I actually got right there. I'm like, 8 times 8, that's 36. 6. But no, I'm just bad at multiplication. All right, boom. I think this is associative. And associativity is hard to check with the tools that we have. It, very often, like a long, grueling process. Let's go ahead and just say yes. Here, the idea is that we understand this term and what it means. Right? Grouping matters, or grouping does not matter, I should say. All right, is the binary system commutative?
I think so.
And I think there's a really easy way to check this one.
Because the Cayley table kind of organizes it for us where we can see the symmetry, right?
Yeah. Like 4, 2, and 2, 4 give me the same thing. And this like diagonal symmetry kind of immediately tells us it's commutative. That one's also now just been proven via exhaustion. We checked every option by filling out the Cayley table. Once again, this table tells us a lot about the structure of the binary system. Right? Is there an identity element? This is always kind of hard to find sometimes. That was a weird sentence. It's always hard to find sometimes.
Yep. I think so.
Oh, I see it. Are there any rows or columns that are the same as the given row or column?
Isn't it 6?
I think 6, right? 2, 2, 2, 4, 4, 6, 6, 2, 2, 4, 4, 6, 6, 8, 8, 6, money, anything is going to return the element that was paired with 6. 6 is our identity, which means we can answer the fifth question. Not 6 factorial, 6. These are all yes factorials, by the way. Lots of yeses. If the answer to the previous question was yes, list the inverse of each element. What is 2's inverse?
2's inverse is 8.
2, yeah. Cayley Taylor's tables, right? Boom. Boom. 2 money 6 is equal to our, 2 money 8 is equal to our identity element 6. All right. How about I've strolled down. Let's actually scroll back up. What is 4's
4
inverse?
4 money 4 is 6.
4 money 4 is 6. 4 is its own inverse. And that leads me to believe that 6 is also going to be its own inverse.
I think so.
Because we're kind of like left with just 6. 6 money 6 is 6. Boom. And these are commutative. Yes, we already proved that the whole thing is commutative, but just as a reminder, the inverses and the identity need to be commutative regardless of if the whole group is commutative. Otherwise, we don't get that final moniker. What is this binary system called?
Group.
It is a group, but more than that.
Abelian.
It's an abelian group. Awesome. All right, here's one more. Let's tackle this one together.
Wait, this is another money?
Yeah, money has now changed. Wait, do you want to change the symbol?
Yeah, this is a star.
Oh, it totally should just be star. Oh, no. This is just bad formatting.
Oh, that's up there.
The question 6 used to be up here. Question 6, is it a group? Yes. And guess what? It's also an abelian group. Yep. All right. New set, new operation. What do we have here? GCF. Greatest common factor of the two things. Is this a group? And if so, is it an abelian group? Want to tackle this chart out together?
Sure.
I'll start bottom right. You start top left.
Okay.
Right, so greatest common factor. Oh, wait, no, that's not what. Yeah, that is what I want. Boom.
Oh, wait. GCF. There's just one.
Oh, I'm kind of cheating here. Oh, no, I'm not. Wait, I'm having a hard time remembering what a greatest common factor is.
Yeah, maybe we should do this together. Okay, so the greatest common factor of 1 and 1 is
hey, everyone, it's okay to like have a flub like this.
Yep.
The greatest common factor. So it's the greatest thing that goes into both numbers, not the least common multiple, which is like messing up my brain.
Yeah.
Yeah. All right. So you have the easy one. I was writing 12 over here. So 1 in any number, the GCF is 1, right?
Right.
All right. I'll get this one right here.
Okay, cool.
Okay.
And then with 2 and 2, their GCF is 2.
2.
Right? And actually, I think all the way down this diagonal, we'll just get the same thing as what is it?
Wait, no, but 3 and 3's greatest common factor is 3, right?
Right.
4, 6, 12, right?
Yeah.
Okay, cool. Okay. 2 and 3's greatest common factor is 1, right?
We're back to 1, yeah.
Yeah. And 3 and 2 similarly 1. Okay. Yeah, this was better done in groups rather than on our left to our own devices.
Better. Okay, GCF of 4 and 2. I think that's 2.
2. Yeah.
And then it's
I'll get this top one.
Sweet.
Yep. All right.
You're doing the upper diagonal or the upper triangular. I'm doing the lower triangular.
Boom, boom. Yep. Right. I'll do this. Okay. 2 and 6. That's still 2, right?
I believe so.
And
2 and 12 still
12, 2. All right, I'm getting the heebie-jeebies about this binary system because there's some like weird patterns happening. Let's keep going.
Well, there's like ones, which is nice. I feel like it's
true.
Kind of like interestingly sparse.
Then it's like 1, 2, 1, 2, 2, 2. I don't know. It's weird. Anyways, 3 and 4. I think that's gonna be 1, right? 6 and 3. That's a 3. 3. Well, we got an odd number finally.
Whoa.
Oh no, I guess we got
3 again.
3. Yep.
One.
All right. 6 and 4. That's gonna be 2.
2. 4, 12.
4.
4.
6 and 12.
Hey.
Okay.
I think that the bottom row makes me very happy.
1, 2, 3, 4, 5. 1, 2, 3, 4, 6, 12. Boop. All right. Is this closed under the operation? Seems as though it is. Right? Did we get any numbers that are not in the set?
No.
No. So we are yes here. Cool. Is it associative? This is the one that's making me feel weird.
Okay.
Is this associative?
I think
proving things are associative is hard. We kind of just have to convince ourselves. But
didn't we like the whole way that we were filling it out? We kind of just like did it associatively. Like we split it up instead of splitting up left and right half. We split it up top diagonal, top triangle and bottom triangle.
That was commutativity though, wasn't it?
Oh, that is commutative.
This is totally commutative, right? Because exactly for that reason, right? We were doing the triangular. This is symmetric about its major diagonal. I just, because of these weird patterns, 1, 2, 1, 2, 2, 2, I think this is not going to be associative. Let's find a counterexample or try to.
4, 3, and I don't know, 12.
All right, and it's star, right? I'm just gonna do a dot. Don't tell anyone. All right, you do the left-hand side, I'll do the right-hand side.
Got it. It's about 1, and I'm gonna go back to star. Maybe I made a bad choice.
All right. Well, maybe you didn't. Maybe it is associative. Let's not pick 12 because 12 is that cool number that you liked.
Oh, true.
I'm feeling maybe 2.
Oh, that's what I was gonna say.
Are we still 1? Maybe it is associative. Yeah. All right. We totally did not just leave and check the answer key. We checked every single possibility here with our super fast brains, and it is associative. I was wrong. My initial assumption. But do you see like why I was a little bit nervous?
Yeah, because it looks weird.
It does look weird. Maybe it's not going to meet something else that the answer key that we did not look at revealed to me. Is there an identity element?
I think so, because a 12 looks like it's pretty happy.
Yeah, 12 looks pretty happy. I like that. I like that. The identity element is definitely happy. Does it work both ways, just to make sure?
I think so. Yeah. Yep.
Right. Does every element have an inverse then? And if so, list them. So what's 1's inverse?
So when we do 1 star something, we get out 12?
Yeah.
Wait, that never happens.
There are not inverses. We have an example of something that meets a lot of the requirements, but didn't meet them all. Hence a non-example. You always need a non-example with a correct example, like we did in the first one. How should I phrase this? There does not exist an inverse for every element.
Okay.
I'm just reading it, not inverse. All right, is it a group?
There doesn't exist an inverse.
There doesn't exist inverses for all elements A in the set. Woo.
Yep.
Wait, is it a group?
No.
No.
Because we don't have the inverse thing.
We have commutativity though, right? Yeah, we do. So we almost got it. We just didn't get it. No group.
That's okay.
And it's not an abelian group either. It's not a non-abelian group. No, an abelian non-group. I digress.
Wait, so are groups a subset of
You see where I was going with that, right? Yeah, an abelian group is a subset of groups.
Abelian group is a subset of groups because abelian groups have more conditions, so it's a smaller set.
Yeah. So I have one last example that's not on here. But my question to you is rock, paper, scissors a group?
Okay, so I think it's closed because you can't ever get something that isn't rock, paper, or scissors as an output.
Okay, so we are closed.
Is it associative? Well, one side is always going to win no matter which matchup you have.
Wait, right? So rock?
Well, except for ties. How do we deal with ties? Rock. Rock.
Rock, we'll output rock, right?
I guess so, but it's 2 rocks because it's a tie.
Closure works. Give me 3 inputs.
Rock, paper, scissors. So then
Great.
Rock, paper outputs paper.
And then wait, paper. What's the symbol for the rock, paper, scissors group?
Let's go back to star because that's what we had in the beginning.
R, P, S. No, can we do BAM?
Sure.
Thanks. So BAM, 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 BAM. Mm-hmm. Not to confuse you with the character from the Flintstones.
Bam, bam.
Twice. What is P, BAM, S?
That is S.
S. Scissors, beats, paper. And then what is R, BAM, P?
R, BAM, P is P.
Paper beats rock because obviously paper covers rock.
Mm-hmm.
Did you know Mr. Stein used to compete in competitive rock, paper, scissors tournaments?
I did.
Yeah. No,
like
the don't have the students.
Awesome.
Yeah. All right. And I think he got to like the final game. We need to ask him. Hey, students, if you see Mr. Stein in the hallways, be like, hey, I heard that you were in a rock, paper, scissors tournament. Can you tell me the outcome? Anyways, R, BAM, S.
Rock
and
scissors. Rock. That's rock.
Rock beats scissors. How about paper and scissors?
Paper and scissors. Paper gets cut by scissors.
Paper gets cut by scissors. Regardless, there's no way we're getting R from that right one.
No.
This is not associative.
Womp.
Is it commutative?
I think so, because if you have the matchup of rock and paper, paper's always going to win, even if the other person is doing paper, because paper is the outcome.
This is the only example I know of a binary system that is not associative, but is commutative. I cannot think of another example. And I challenge everyone out there to find an example for us of something that is is commutative, but not associative. This is the only example I know. And with that, Finny?
Well, let's see who gets to close it out.
Rock, paper, scissors, shoot. I did this. I'll be honest. I know, yeah, you beat me twice with the same thing. According to The Simpsons, rock always wins.
Because I never know.
Rock always wins according to Bart Simpson.
Start, so I always do rock first.
That's a good point.
Now you know how to always beat me.
All right, but can we do it one more time?
All right.
Rock,
paper,
scissors, shoot. Ah! You fool.
But you have the paper out already.
Run, you fools. All right, let's close this one out. It's all you.
Oh, because I won twice.